up until now, we have written a rate law as follows. This would be a first order reaction. Its rate equals rate constant K times the concentration of a reactant A. And you notice that time has nothing to do with this. So what you're seeing is the rate at a very specific moment in time. So this is the rate law for a first order reaction that is time independent. This means that time is not a part of the equation. So this equation is for a specific moment in time. Now we're going to introduce a rate law that tells us how concentration, that's the square brackets, changes with time. This is called the integrated rate law. For a first order reaction, this is, and it looks like a scary equation, but just remember, it's just plugging in numbers and using the ln button on your calculator. So what it says is the natural log of A, of the concentration of A, minus the natural log of the beginning concentration of A. So A is at some ending point and A0 is at the beginning. It means initial concentration. That's going to equal the negative of the rate constant times time. So two things you notice about this. Well, let's go ahead and read this. Concentration of A is the concentration of the reactant at a particular time. A0 is the initial concentration. This means the concentration at the beginning of the reaction. It doesn't necessarily have to be that, though. It can be the concentration in the middle of the reaction at some point that you want to start measuring. So you can start measuring somewhere in the middle of the reaction and then take your final measurement for A later on in the reaction. But we're just going to think of it as the concentration at the beginning of the reaction. And then T is the time that we're interested in knowing for this change in concentration. So that's a change in concentration going on there. So two things you notice. There are two different values of A, a beginning value and an ending value. And also you notice that time is a part of this equation. So let's give you an example. The rate law that we studied in the previous lesson, we just learned is like a speedometer in a car. It tells you how fast you're going at an exact moment in time. It tells you how fast you're going at exactly the moment that you look at the speedometer. It doesn't tell you how fast you're going 5 seconds before, 5 seconds after, or for the entire trip. It just tells you how fast you're going at exactly the moment you look at the speedometer. So in physics, you call this the instantaneous velocity. The integrated rate law includes the variable time. It tells you how long it took you to drive between two places, such as San Diego to Los Angeles. In physics, you call this the average velocity. So it has two different locations, a beginning point and an ending point, and then you measure how long it takes to go between those two. So that's what the integrated rate law is going to do. An integrated rate law incorporates time into the equation. The rate law we have been working with so far does not have a time variable. So the rate law we have been using tells us how fast a reaction is proceeding at a specific point. For example, what is the rate of the reaction at that point right there? The integrated rate law using time tells us how long it will take for the reaction to go from some beginning concentration of A0. And again, A0 doesn't really have to be right at the beginning of the reaction, but let's just say it is to keep it simple. From the beginning concentration A0 to some final concentration A. For example, from A0 to A. So that's going to take a certain amount of time, and that's what integrated rate law allows us to deal with. A first-order reaction rate curve can be converted into a straight line using the following equation. And you don't need to understand the math involved. So remember what a first-order reaction is. It means as you double the concentration, you'll double the rate. The rate will go twice as fast. Not twice as much time, but twice as fast, so it'll be less time. If you triple the concentration, the reaction will run 3 times as fast. If you multiply the concentration by 5, then the reaction will run 5 times as fast. That's what a first-order reaction is. So there's the equation for this. So if you look at on the left, the graph on the left, that's the actual graph of the concentration versus the amount of time. That's what we saw way back at the beginning of this unit on Monday. It's what that curve actually looks like. It's steeper at the beginning because there's more reactant to molecules or atoms to bump into each other to break apart to create the reaction. As you use up the reactant, as time goes by, then the curve becomes flatter. It becomes less steep because the reaction will not take place as fast because there's not as many reactant molecules. So what the natural log allows us to do is turn that into a straight line. We talked that logs do two things. They allow us to bring a range of values that you couldn't possibly graph because they're too far apart, like 1 to 1,000,000, down to a more reasonable, manageable number. That's not really what we're interested in logs in here in this lesson. We're more interested in how they create straight lines here. So there it is. So the natural log of A minus the natural of the final concentration of A minus the natural log of the beginning concentration of A equals the negative of the rate constant times T. So what's really nice about this is that the slope of that line on the graph on the right, the slope of that line is the rate constant. It's how fast that reaction is taking place. So this equation can be rearranged by adding the ln A0 term to both sides. So watch what happens here. So we added ln A0 to both sides. Now it says ln, natural log of the concentration, ending concentration of A, equals negative KT plus ln of the initial concentration of A. In a second, you'll see why we did that. The graph on the left shows the actual decrease in a reactant in a first-order reaction plotted against time. The graph on the right shows the natural log, ln, of the concentration plotted against time. This graph forms a straight line where the slope is the negative of the rate constant, so it's negative k. The rate constant is always a positive number, but that slope is a negative slope, so it's a negative of the rate constant. So the equation is in the form of a straight line. If you look at that, the reason we added that ln A0 to the right side now is because now it forms what you remember from math class. Y equals mx plus b. M is the slope, x is the independent variable, in this case that's the time, and b is the y-intercept. Okay, so that goes back to integrated math 1. If we put a value in for t, we will get ln A, the natural log of A. However, we're interested in the concentration A, not the natural log of the concentration of A. So how do we deal with that? How do we get that concentration of A, square brackets A, out of the ln? Well, you might remember we learned some principles of logarithms and exponents. And we use E, that's the exponential, that's Euler's number, to take the inverse of ln A. So on your principles of logs that we did back in lesson 2 and in the previous lesson, if you take that ln A and you make it an exponent of E, then remember E and natural log are inverses of each other. They undo each other. So if you take ln A, put it in the exponent of E, you end up getting A out, the concentration A out. And also the slope of M up there in that equation is negative K. So K is the rate constant. The rate constant has to be a positive number. So the negative sign is the slope, but the actual rate constant is the positive. So this shows a concentration versus time of a first order reaction. This is the curve we're used to seeing for the concentration of a reactant that is being consumed. Over on the right, this is the natural log of the concentration versus time of a first order reaction according to the equation that we just saw. This graph allows us to see a first order reaction as a straight line and determine the rate constant K. So now we're going to go into a problem here. We're going to do the decomposition of SO2Cl2 produces SO2 and Cl. So it's a very simple reaction. The SO2 and the Cl2 just simply come apart and become an SO2 molecule and a Cl2 molecule. At a certain temperature, the concentration of SO2Cl2 was monitored as a function of time. A plot of the natural log of the concentration of SO2Cl2 versus time in seconds produced a linear straight line plot with a slope-intercept equation given as y equals negative 0.000301x minus 0.200. What is the order of the reaction? So think about that. What's the order of this reaction? Well, you might have guessed it's first order because that's the only one we've talked about so far, but why? The answer is it's a first order reaction. So read the question carefully. The information says that a plot of natural log of SO2Cl2 versus time produces a straight line with the equation shown. This is a negatively sloping equation. We do not need to know the specific numbers to answer this. So the key is if a plot of lna versus time produces a straight line, then the reaction is first order. So if you go ahead and you take the concentration and then you take the natural log of it and you plot that against time, if you end up getting a negatively sloping straight line, then it's a first order reaction. If you don't, then it's not a first order reaction. Okay, there's the same question. Now it's asking what is the rate constant. So look at that equation. What's the rate constant? That's K. The answer is the slope M is the negative of the rate constant. So M equals negative K. So therefore the rate constant is K is a positive number. Okay, and note, rate constants K are always positive numbers. So the rate constant, don't get tricked on that. It's not negative 0.000310. It's positive 0.000310. Okay, same question. So now question number 3 down there is at the same temperature. The key to that is your temperature must stay the same in a kinetics problem, because if it changes, then your value of K, your rate constant, changes, and we're going to learn what the variables are that go into the rate constant, but one of them is temperature. If your temperature changes, the rate constant changes, and then your entire equation is invalid. It won't work. So at the same temperature, 0.200 molar of SO2Cl2 is decomposed. So a decomposition reaction is where a single reactant breaks into two products. So look up at the very first sentence up above. That's what it's saying. Decomposition of SO2Cl2 produces SO2 and Cl2. So it broke in two. In other words, it broke into two pieces. So that's a decomposition reaction. So the question is, what is the concentration of SO2Cl2 that remains after 5 minutes? And I give you a hint there that you have to convert the minutes to seconds. Okay, everything here is in seconds. So what do we do? Well, what we do is we simply plug in the number. Answer, the temperature must stay the same or the rate constant will change. That's what I just mentioned. So the concentration, the initial concentration of SO2Cl2, you notice the little zero there after the square bracket means that it's initial concentration. What the zero means at time equals 0. When you're just starting your stopwatch on this equation, that's what the concentration is at the beginning of the problem. This is the initial concentration of SO2Cl2. T equals 5 minutes, which equals 300 seconds. Time is measured in seconds in this problem, so you need to make that conversion. So using the equation, you plug in the numbers. Convince yourself that the numbers are plugged in properly for that. You need to take the natural log of the 0.2 molar initial concentration. And if you do the numbers on that, there's the same equation. You go ahead and do the calculation. And what you'd get is the natural log of SO2Cl2 equals, everything on the right side was simplified, and it equals negative 1.702. So that's what the natural log of that is. But we're not interested in the natural log of SO2Cl2. We're interested in what is the concentration of SO2Cl2. So again, you use your little manipulation with E and natural log, the inverse, to get that SO2Cl2 out of the natural log. So you do that. That means you also have to raise negative 1.702 to the e to that power. So you raise E, take E on both sides and raise E to the power of what you see there. Okay, so the SO2Cl2 comes out. And if you do on your calculator E raised to the negative 1.702, you get 0.18 molar. So that's the concentration of SO2Cl2 at 5 minutes into the reaction. That's how much is left. It's not how much was used up. Sometimes students make that mistake. They think that's how much is used. No, it's how much is left. So you started with 0.200 and you ended up after 5 minutes with 0.18. And there that is. So that answered the question. What is the concentration of SO2Cl2? Okay, here's question number 4. The data up above is the same. What is the concentration of the products SO2 and Cl2 at 300 seconds? So we figured out what the concentration of the SO2Cl2 was at the end of the 300 seconds. Now they want to know what's the concentration of the SO2 and of the Cl2, of the products, after the reaction has taken place. So answer, we assume that we started the reaction with no SO2 or Cl2. This is a fair assumption in chemistry problems when we are not given initial concentrations of products. So the balanced equation is very simple. You take SO2Cl2 and it decomposes. It comes apart into SO2 and Cl2. And you can see that that's balanced, which means you start with, for every 1 mole of SO2Cl2 you start with, you end up with 1 mole of SO2 and 1 mole of Cl2. So the initial concentration of SO2Cl2 was 0.20 molar. The final concentration that we figured out in the last part, it went down to 0.18 molar. So the amount of SO2Cl2 that was consumed is the initial concentration minus the concentration at the end of the 5 minutes. So that's 0.2 minus 0.18, and that gives you 0.02 molar. That means 0.02 molar of SO2Cl2 was used up or was converted into SO2 and Cl2 over on the right-hand side. Since we see it's a 1 to 1 to 1 molar relationship in the chemical equation there, in that balanced equation, then the equation tells us that 1 molar of SO2 and 1 molar of Cl2 was produced for every 1 molar of SO2Cl2 used up, or 0.02. So you end up with 0.02 molar of SO2, and you end up with 0.02 molar of Cl2. So 0.2 molar of SO2 and 0.2 molar of Cl2 was produced in 5 minutes. Okay, now we're going to talk about a concept of half-life of a first-order reaction. Half-life is the amount of time it takes half of the concentration of a reactant to be consumed, to be used up. What defines a first-order reaction is that no matter what the concentration of the reactant present, the time it takes for half of it to be consumed is always the same. And that's, most reactions are first-order reactions, so this is true of most reactions. So let's see some examples here. Assume that each of the time interval in the graph is 1 minute. So down below you have the time interval on the graph there is 1 minute, 2 minutes, 3 minutes. Then each minute, half of the concentration of the reactant at that time will be consumed. Key, this is true only of first-order reactions. For all other reactions, the amount of time it takes to consume half the reactant depends upon the concentration. So let's say we start with 100 molar of some concentration of A. After 1 minute, it goes down to half of that, or 50 molar. So from 0 to 1 minutes, it dropped by 50 molar, from 100 down to 50. That's half of 100. Now from 1 to 2 minutes, it doesn't drop another 50. It drops half of what's left, and that's half of 50. So half of 50 is 25. So from 1 minute to 2 minutes, it would have gone down to 25. From 2 minutes to 3 minutes, it would have gone down by half of 25, which is 12 and a half. So 25 minus 12 and a half is 12 and a half. So at 3 minutes, it would be at 12 and a half. And from 3 minutes to 4 minutes, it would have gone down by half of 12 and a half, which is 6.25. So from 0 to 1, it went down by 50. From 1 to 2, it went down by half of 50, or 25. From 2 to 3, it went down by half of 25, or 12.5. And from 3 to 4, it went down by half of 12.5, or 6.25. So every even time interval, in this case 1 minute, it's going to go down by half of what the current concentration is. And that's true only of a first order reaction. So there's a simple formula to determine the amount of time one half-life is for a first order reaction. It's simply you take 0.693 over the rate constant K, and that will tell you how long a half-life is of a first order reaction. And I'll give you some of those problems to work in the assignment. They're just simple plug in the number problems. Alright, so let's see an example here, similar to the one I just gave you. Example, a reactant has a concentration of 8 molar and a half-life of 1 minute. What will be the concentration of the reactant be? What will the concentration of the reactant be after 3 minutes? So answer, the half-life of 1 minute means that the existing concentration will be reduced by half for each minute that passes. So if you start at 0, you have a concentration of 8 molar. 1 minute later, you have half that. You have 4 molar. After another minute, from 1 to 2 minutes, half of the 4 goes away, and that becomes 2 molar. And then from 2 to 3 minutes, half of the 2 disappears, and that becomes 1 molar. So the answer is there will be 1 molar remaining after 3 minutes. So don't keep cutting the 8 in half. That's just your starting value. You cut that in half for the first minute, but don't keep cutting 8 in half for each additional. It's whatever is left at that point you cut in half. So example, what is the half-life? What is the half-life of a first order reaction that has a rate constant of K equals 2.3 times 10 to the minus third 1 over seconds? Okay, that's the unit of measure there. So there's a simple formula to determine the amount of time of one half-life. And there it is. You saw that on the previous slide. So they give you the rate constant, so it's going to be 0.693. That's a constant number for these first order half-life problems. It never changes, 0.693. But the K is what you put in. That's what varies down below. And if you do the math on that, you come up with 301 seconds or 5 minutes. That would be the half-life. Now we're going to get into second order reactions. These are not nearly as common in nature and in chemistry as first order reactions, but they do happen, and so we should understand them. So the curve of a second order reaction on the left, that's the one on the left, it looks similar to a first order reaction curve. It goes down fastest at the beginning because there's more reactant, molecules and particles bumping into each other to break apart to create the reaction. But as you start to run out of the reactant, less and less of it, the reaction curve gets less steep, it gets flatter because the reaction doesn't happen as fast. Remember, steep curve means it's happening fast, flatter curve means it's happening more slowly. The way to tell the difference is to plot the graph of 1 over the concentration A versus time. If the plot produces a straight line on the right with a positive slope, then the reaction is second order. Okay, so what you would do here is you got this curve. You say it might be first order, it might be second order. I'm not really sure. I can't really tell. So what you can do is plot ln of the concentration A versus time for this curve, and you would find out it doesn't produce a negatively sloped straight line. Remember, that's what we said a first order reaction has to do, a negatively sloped straight line. You say, okay, it's not first order. It didn't produce a negatively sloped. I don't know what shape it would have produced if you did that, but it didn't work. It didn't produce the straight line, so it didn't work. So now you go and you say, okay, well, maybe it's a second order reaction. So you're going to plot 1 over that concentration that's on the left-hand graph versus time. And you find, hey, it produces a straight line that's positively sloped. That means that's the characteristic of a second order reaction. It produces, when you plot 1 over A, 1 over the concentration of A versus time, it will produce a straight line that's positively sloped. That's very distinctive. That means it's a second order reaction. If neither of those plottings that you just did produced any kind of straight line, then it just means it's simply neither first order or second order. That is a possibility. And there you see what you're plotting. So again, the actual plot of the concentration versus time is on the left, the same way we did it with the first order. But now what we're doing is we're plotting 1 over the concentration of A. No natural logs involved here. Did you notice that? You don't have any natural logs involved here. It's just 1 over the concentration of A versus time. That will give you a positively sloped straight line, and that means it's a second order reaction. Remember, what does a second order reaction mean? It means as you double the amount, the concentration of the reactant, you quadruple 4 times the rate. So you double the concentration of the reactant, then the reaction doesn't go 2 times faster, it goes 4 times faster because it's a square. That's what a second order reaction is. Okay, so we can do the same thing that we did in the last in the last section where we were talking about first order reactions. The equation to create a linear equation from a second order reaction is 1 over the concentration of A equals K. Notice it's a positive K, means it's a positively sloped line. That's the M, that's the slope, times T, the time, plus 1 over the initial concentration of A. So in this equation, K is positive and the line has a positive slope. Okay, and the equation for the half-life of a second order reaction, should say second order reaction, is there it is. It's the half-life is 1 over the rate constant times the concentration. So that means the half-life, unlike a first order reaction where the half-life was always exactly the same amount of time, 1 minute, 1 minute, 1 minute, it's not going to be here. It's going to depend on the concentration. So as the concentration gets smaller, as the concentration gets smaller, then the half-life is going to get longer and longer. That's because the reaction won't happen as fast. So the half-life of a second order reaction depends on the beginning concentration A naught. As the concentration A naught gets smaller, the half-life gets longer, so it takes more time to use up the reactant. Okay, finally we're going to touch on a zero order reaction. So the rate law for a zeroth order reaction is rate equals rate constant times the initial concentration raised to the 0 power, that's what zero order means, the exponent, which simply equals K. So in other words, the rate is simply K, and it's a negatively sloped line. So the rate is going to be a function of nothing. It's going to be what it is, and it doesn't change. So whether I'm at a high concentration up here, the rate constant is going to be the same. The rate is going to be the same. It doesn't change. So the thing you need to remember about a zero order reactant is the rate equals the rate constant, means that the concentration of the reactant does not affect the rate of the reaction, because you don't see the concentration anywhere up there. Rate equals K. Whatever that is, it never changes. So concentration has nothing to do with the rate for a zeroth order reactant. The concentration will decrease at a constant rate, straight line. So you're simply plotting the concentration versus time, and it goes down at a Alright, so the order of a reaction can be determined by creating a table and graphing the time versus each of the functions that create a straight line for zeroth, first, and second order. So the order can be determined as follows. If it's zeroth order, the time versus the concentration is a straight line with a negative slope. In other words, concentration doesn't affect the speed of the reaction at all. It's just going to be a straight line with a negative slope, and that is a zeroth order reaction. If it's first order and you plot the time against the natural log of the concentration, and that's a straight line with a negative slope, then it's a first order reaction. And finally, second order, if the time versus 1 over the concentration, no natural log involved there, is a straight line with a positive slope, then the reaction is second order. If none of these produces a straight line, then the reaction is none of these orders. It doesn't have to be any one of those, but in the problems you'll be doing in this class, it will be. Alright, so let's do a problem here. The decomposition of gas A is monitored as a function of time at a certain temperature. Again, the temperature has to be fixed. The plot of 1 over a versus time produces a linear straight line plot with the equation that you see there. So the question is, what is the order of the reaction? Well, 1 over a versus time produces a straight line, first of all, and second of all, you can see that the slope of that, 0.0296, is a positive number, so it's a positive slope. So positively sloped straight line, when you plot 1 over a versus time, it means it's going to be a second order reaction. So since the plot of 1 over a versus time produces a straight line, the equation above is the equation for a straight line with a positive slope, then the reaction is second order. Okay, same question there. What is the rate constant? So hopefully by now you can spot that. The rate constant is the slope of the line, which is 0.0296. That's a positive slope. Okay, so there is the same equation. 3. Beginning with 0.10 molar of A, that's the initial concentration, what percent of A will react after 5 seconds? So this is kind of like the previous set of questions, but it's asking a little bit different. What percent of A will react, not just the amount. So beginning with 0.1 molar of A, what percent of A will react after 5 seconds? So you enter the values in. There's the equation. You put T equals 5 seconds. And there's the numbers. Be comfortable that those are the numbers that should be put in there. And now you just go ahead and compute that, and you get 1 over A equals 10.148. Of course, we're not interested in 1 over the concentration of A. We want to know the concentration of A. So to get that, you take the reciprocal of 10.148. Okay, so there we go. Same question. Everything there is the same. There's the equation again. And so what you will get is concentration of A is 0.0985 molar. So this is the concentration of the reactant that's remaining after 5 seconds. Remember, that's not the amount that was used up or consumed. That's the amount that's left. So you started with 0.100 and you ended up with 0.0985 of the reactant. This means that 0.100 original concentration minus 0.0985 molar equals 0.0015 was actually used up or consumed in 5 seconds. So the question wants to know what percent of A will react after 5 seconds. React means it was consumed, it was used up. So that's the 0.0015 number. So if you take that number, 0.0015, and you put it over the original concentration, 0.1, and multiply that by 100%, you will get 1.5%. So 1.5% of the reactant was consumed or reacted in 5 seconds. All right, so that takes care of this. It was a lot. It was a lot. How do you study this? You write these examples down as you watch the video. Don't just watch it. You're not watching TV here. You're studying. You write these examples down and you do them a second and a third time until you can do them smoothly without looking at the video. It's the only way to get good at this is repetition, just like it's the only way to get good at anything. So you got to be willing to put the time in to do that. Once you can do that, move on to the assignment problems. Yes, it takes time to do that, but it's just the only way you learn this. There's no shortcuts to learning this. We are under a tremendous time crunch to get this done, but you've got the time, okay? You're at home all day and use that time, all right? Okay, so we've got one more lesson for this, and I'll go ahead and get that up online as soon as possible and study this really intensely because it is an AP level subject, okay? So we'll see you on the next lesson.